I don't know how you're feeling at this point in our journey through modern cosmology. I'm guessing you might be puffing and panting a little bit from the exertion. We've had some fairly steep climbs, and some of the going has been quite tough in places. So you'll be pleased to hear we've now reached a perfect place to sort of sit down, get out our sandwiches and catch our breath. Because in this lecture, we are not going to be moving into any significantly new territory. And instead, I want to pause to gather together some of the topics that we've already encountered and focus on a rather specific aim. You see, throughout this course, I've often referred to particular numbers that measure the properties of the universe. Things like its expansion speed, or its age, or its composition. Actually, there are about a dozen of these so-called cosmological parameters. But we've never really considered all these numbers together as a single group, and nor have we really looked carefully at how they've all been measured. So that's going to be the aim for this lecture, getting a handle on the universe's vital statistics. Now, I know it may not sound too exciting to be chasing down a dozen or so numbers, but as you'll see, the effort to find them has turned out to be a fabulous success story, and it's the primary reason cosmologists are now feeling so optimistic about the state of their subject, why they feel cosmology has come of age, finally. So let's start off gently by quickly reviewing the 6 key pieces of evidence that point to the fact that we live in an expanding, evolving universe that began in a hot Big Bang a few billion years ago. So first, galaxy redshifts show that the universe is expanding, and naively extrapolating the expansion backwards suggests it began about 14 billion years ago. Second, when we measure the ages of things, stars or galaxies, we find all ages up to about 12 to 15 billion years, but nothing older has ever been found. Third, looking way out into the universe and therefore way back in time, galaxies appear younger. It really does seem as though the contents of the universe are systematically aging. Fourth, we observe an extremely uniform microwave background that has an accurately thermal spectrum, suggesting it came from a hot, smooth, early phase. Fifth, the microwave background also has slight patchiness that over time can yield the patterns of galaxies that we find around us today. And finally, as we learned in the last lecture, helium has 25% abundance almost everywhere, even in the oldest stars, suggesting it was formed in the hot Big Bang itself. Now, in addition to these observed properties, we also have what seems to be an extremely robust theoretical framework for describing the universe. We start with Einstein's theory of gravity and use it to follow the expansion of a homogeneous distribution of matter, radiation, and dark energy. The Friedmann equation tells us how the universe expands with time, and therefore how the density and temperature of these components drops with time. The theory also includes slight fluctuations, roughness, superimposed on the homogeneity, and it's possible to follow this roughness using a computer to see how it grows and to form structures, from the first stars to galaxies to the web-like pattern of thousands of galaxies. Now, this theoretical cosmological model contains a number of parameters, and it's these that we're trying to measure. See, the overall game is to vary the parameters of the model universe until we find the best match to the observations of the real universe. And when that match has been found, then in a sense we've measured these parameters for the real universe. Now, of course, the whole game only works if the match is at least reasonable, but as we'll see, it is in fact remarkably good. In the end, the best fitting parameter set defines what cosmologists call the concordance model, meaning this particular model is in concordance with all the observational data. So, here's what we're going to do. First, we'll look briefly at the parameters themselves with their current best estimates, their concordance model values. Then we'll look at the 5 key observational data sets that are used to compare to the models. Then we'll look at the nature of those comparisons in more detail, and by the end of all of this, I hope you'll see why this game of finding these parameters has really brought the subject alive. So let's start by listing the primary cosmological parameters. You've met most of them before, but it's nice to gather them together into a single group. The most famous, of course, is Hubble's constant, h0, which gives today's rate of cosmic expansion. Its value is 22 kilometers per second per million light years. Next come the current densities of the 5 cosmic constituents. Here they're given in units of hydrogen atom masses per cubic meter. From largest to smallest, we have dark energy, dark matter, atomic matter, photons, and neutrinos. Now remember, there is that important reference density lurking here, the critical density. It's the density that makes the universe's geometry Euclidean, or flat. Here's its formula from lecture 10, and plugging in 22 kilometers per second per million light years for h0 gives a critical density of 5.8 hydrogen atom masses per cubic meter. So, when we divide our component densities by 5.8, we now convert them to their omegas. Here they are, 0.73, 0.23, 0.04, and much smaller values for radiation and neutrinos. The total omega is 1.00, which tells us that the universe's geometry is indeed Euclidean. Moving on, the next cosmological parameters deal with the presence of roughness in the universe. And there are 2 important ones here, an amplitude, A, and an index or slope, N. Remember from lecture 17, cosmologists quantify roughness using a graph that we've called the roughness spectrum. Here's a sketch of it for today's universe. It has a peak of maximum roughness near 200 million light years, and it's smoother on both larger and smaller scales. And you remember also that the peak comes because the growth of small-scale structure and roughness was suppressed during the radiation era, before 60,000 years. So the initial spectrum before suppression is more like this straight line. The 2 roughness parameters are the slope of this line, n, and how high it is, a. Now, to be complete, I should mention one more parameter that we've not talked about before, and it concerns the nature of dark energy. I've always suggested this energy is fixed. It doesn't change as the universe expands, which is what we expect if it's a true energy of space, as a vacuum energy. But since we don't really know what this actual nature is, a much more cautious approach is to allow for the possibility that dark energy's density might change with expansion. Now, cosmologists do this using a parameter that they call W. It's really very straightforward. As the universe expands, if W equals -1, then dark energy is constant. If W is less than -1, then dark energy increases. And if W is more than -1, then dark energy decreases. Now, as you can see, its value has already been measured to be close to -1, and so many cosmologists assume that it really is -1, and that the density of dark energy is constant during the expansion. Now, in addition to these primary parameters, there are 4 other secondary parameters that I think you'll recognize. They're all times. The time when the density of matter and radiation were equal was near 57,000 years. The microwave background formed at 380,000 years. The first stars formed at 400 million years, and the current age of the universe, the time since the Big Bang, is 13.7 billion years. Now, at this point, I haven't mentioned how accurate all these numbers are, and we'll get to that a bit later, but just to give you some idea, most of these numbers are known to somewhere between 5 and 10% accuracy. Some are a little better, some a little bit worse. So let's now take a look at the 5 primary observational data sets that are used to measure these parameters. We've met them all before, but we've not really viewed them all collectively. Ultimately, as we'll see in a minute, it's the combination of all of these data sets that provides such a powerful way to measure all the parameters. So first data set includes all the distance measurements to nearby galaxies. Remember in lecture 6, we looked at the various methods to do this, but perhaps the most critical have been those Cepheid variable star distances measured using the Hubble Space Telescope. That whole project culminated in an estimate of the Hubble constant. You can see the classic distance redshift graph, whose gradient, or slope, gives the value 22 kilometers per second per million light years, with about a 7% uncertainty. Now, the second important data set is an extension of this first one and includes distance measurements to remote galaxies using those white dwarf supernovae. Of course, by looking very far away, one is looking long ago, and so it's possible to probe how the expansion rate has changed in the past. Remember from lecture 9, the surprise 1998 result that the expansion was slower in the past, so the universe's expansion has been speeding up. It's accelerating. Now, since that time, many more supernovae have been found, and here's the kind of plot you can construct using the data. Time is along the x-axis, with today at 0 near the middle. And the y-axis is scale factor, S, the relative size of the universe. So it's 1 for today. Now, the redshift of each supernova tells us the scale factor when it went off, and its brightness gives us a distance from which we can figure out the look-back time when the supernova went off. So these data allow us to construct our old familiar curves of S of t, how the scale factor changes with time. Now, remember from lecture 12 that the Friedmann equation tells us exactly how this graph should look as long as we specify 2 key numbers, omega dark energy and omega matter, where omega matter is the sum of dark matter and the atomic matter components. So here are some of those classic curves of S of t. Here's a dense universe with omega matter of 8 that quickly recollapses. Here's a flat universe with omega matter unity but no dark energy, so it's always decelerating. Here's an empty universe that just expands at a constant rate, no acceleration or deceleration. Now notice none of these match the data, which clearly lie above the simple coasting universe, indicating acceleration. Well, you can see the method here. Using the Friedmann models as a guide, the data rule out a whole set of possible universes, but the data do fit quite well a Friedmann model with omega matter about 0.3 and omega dark energy about 0.7. And so, in a sense, these 2 parameters are now measured. Let's turn to the third key data set that's used to measure the universe's parameters, the microwave background. Remember from lecture 13, the microwave background shows us the universe just 380,000 years after the Big Bang, when the hot gas had cooled below 3,000 degrees and turned from a glowing fog into a transparent gas. And remember, we look out through the transparent universe to see all around us this foggy wall of glowing gas. Its bright orange light redshifted enormously as it crosses the universe, arriving as in the microwave part of the spectrum. Microwave telescopes, such as the WMAP satellite, find the microwave sky to be extremely uniform, the same in all directions, suggesting that the gas at that time was quite smooth. Its spectrum has a perfect thermal shape with a temperature of 2.725 Kelvin with only 0.1% uncertainty. Now this immediately tells us the energy in photons, and hence the important cosmological parameter omega radiation. Now also, because we understand the physics of how the fog cleared, we know it happened when the universe was 3,000 degrees, and hence the scale factor S must have been about 1,000th, and this in turn pinpoints the time of the microwave background to 380,000 years. If we also fold in our knowledge of omega matter, we then find the great transition between radiation and matter dominance took place around 57,000 years. But most of the information in the microwave background, of course, is stored in its slight patchiness. When we contrast stretch that uniform all-sky microwave image, we get the now classic mottled all-sky sphere, showing regions of slightly higher and lower density and temperature. These are the peaks and troughs of huge sound waves from which the web-like pattern of galaxies will ultimately form. Now remember, from lecture 15, cosmologists quantify this patchiness by casting it as a sound spectrum. Here it is. The amplitude of the sound waves is up the y-axis, plotted against their size, with small waves, that's high pitch, on the right. It has a remarkable shape with a fundamental peak and several higher harmonics, rather like a musical instrument. And just like a musical instrument, the sound of the universe depends sensitively on its properties. So as we learned in lecture 16, the exact form of the sound spectrum can tell us a great deal about the universe's properties. Remember the metaphor I used in lecture 13. The patches on the microwave background are like the DNA of the universe. They're influenced by its past, and they help determine its future. Studying these patches is to cosmology what the Human Genome Project is to the life sciences. Here are three of the most obvious features in the sound spectrum that are affected by the cosmological parameters. The location of the first peak is sensitive to the geometry of space, and so it gives us omega total. The strength of the first peak is sensitive to the total amount of matter, so it gives us omega matter, while the relative strengths of the second and third peaks is sensitive to just the atomic matter, and so that gives us omega atomic. Now here's an example that shows how the patchiness changes from a universe with only 1% atomic matter to a universe with 10% atomic matter. The small-scale roughness is stronger, which of course shows up very nicely in the sound spectrum, where the blue line is for the atomic-rich 10% universe, with its stronger, higher harmonics. Just to alert you here, these spectra have an exponential frequency scale, so they look a little different from that previous graph. Here's a second example that shows the data from the real microwave background and the concordance model fit in red, with omega matter 0.27 and omega dark energy 0.73. It's a fabulous fit, but look how it's ruined if we leave out the dark energy, which is the blue curve. See, it's this sensitivity to many of the cosmological parameters that makes the microwave background such a key player in this whole game. Let's now look at the fourth data set, galaxy redshift surveys. Here are sections from three of the most well-known surveys, the CFA survey, the Anglo-Australian 2DF survey, and the Sloan Digital Sky survey. Remember, each dot is the position of a galaxy. And you can see the characteristic web-like patterns with walls and sheets and voids scattered about. And here are the equivalent sections taken from the Millennium Computer Simulation. Remember, these simulations follow the gravitational motion of billions of particles, and they help to understand how galaxies formed and gathered into the clusters and the web. As you might guess, the most important cosmological parameters that affect the growth of large-scale structure are the input initial roughness spectrum and the density of matter. So let's briefly look at these two now. Here's a set of simulations with omega matter, that's the density of matter, increasing from 0.1 to 0.5. Not surprisingly, the simulations with higher density end up with more structure because gravitational aggregation is faster at higher density. In fact, just eyeballing these pictures allows you to guess that the middle of the range roughly matches the real galaxy maps. But of course, the proper way to make the comparison is to use the roughness spectrum. Here's a set of calculated roughness spectra from the simulations with the same range of omega matter. And the real galaxy data clearly single out omega matter near 0.3. You may be wondering what those wiggles are. They're called baryon oscillations, and they're the relics of those acoustic harmonics seen in the microwave background sound spectrum. The slight excess roughness at the harmonic peaks survives until today and is etched in the pattern of galaxies. These baryon oscillations, in fact, allow very precise measurements of several cosmological parameters, and I'll have more to say about them in Lecture 35 when we look at major observational projects for the future. The fifth key data set we just met last lecture. It's the abundance of the light elements: deuterium, helium-3, helium-4, and lithium-7. Remember, these nuclei are made about 3 minutes after the Big Bang, and their abundances depend on the density of the gas at that time. Here is that dependency, and by matching the observed abundances, we found a density near 10 grams per cubic meter. When we convert this to today's density, we get omega atomic of 0.04 with about 10% uncertainty, which of course confirms that atomic matter is only a minor cosmic component. Now, at this point, you may think that the story is over. We've used our data sets and models and measured a number of the fundamental parameters. But in fact, the whole game is much more interesting than that. You may have also noticed that some of the parameters could be measured by several data sets, several different data sets. And so this offers an extremely important possibility, which is to check whether they all agree. Is there a single set of parameters that fits all the data sets simultaneously? So let's have a look at that now. In this diagram, we have two of the most important parameters: omega matter along the bottom and omega dark energy upwards. Each point in this plane specifies a particular universe. For example, those for which omega matter plus omega dark energy is 1 have flat geometry. They lie on this line. Now let's take the supernova data. Because there are uncertainties in the data, we have a region of acceptable values. The true values are more likely to lie in the dark inner region and less likely outside that. Notice that the region is elongated and tilted. This particular method is sensitive to the difference between omega matter and omega dark energy, but it's not so sensitive to their sum. Now let's consider how the model fits to the microwave background sound spectrum. Well, it's a huge relief to see that the regions of high confidence do actually overlap. But notice how the microwave background data is sensitive in a completely different way to the two parameters. So the acceptable region lies at a different angle. As you can see, combining these two data sets gives a much more precise measurement of omega matter and omega dark energy. Let's finally add the redshift survey dataset on galaxy clustering. It has yet another kind of sensitivity to the two parameters, so comes in at yet another angle. And just look at that match. All three datasets overlap in a tiny region. They really nail these two parameters. Now, this convergence on a single unique value from completely different datasets happens again and again. It's an incredible indication that the entire approach is valid and robust. I'll just show you two more examples. Here's a sequence of models with different omega atomic, with their comparison at the top to the microwave background sound spectrum and at the bottom to the galaxy roughness spectrum. Now, the thing to look for is that when the match is best at the top, it is also best at the bottom. The same value of omega atomic is singled out for both data sets. What is that value? Have a guess. It's 0.04, exactly the same as the value we got from yet another data set, the light element abundances. Okay, here's my last example. Our two parameters this time are omega total, which tracks the curvature of space with Euclidean at unity, and up the y-axis is the age of the universe in billions of years. WMAP's first year of observing the microwave background excludes everywhere except the white region. And adding 2 more years of data narrows it down further. Now bringing in the galaxy redshift surveys further narrows it down. And of course, this is all consistent with the age estimates of the oldest stars in the galaxy. Notice that the final region really does suggest we live in a universe with Euclidean geometry and that the Big Bang really did happen about 14 billion years ago. Now, although I've shown you a few examples of fitting models to data sets, in reality, all these fits are done essentially together in one huge match between models and data. And as you saw a minute ago, it's the fact that each parameter must conform to several data sets that really allows most of them to be measured with such high precision. Well, let me end this lecture by once again stepping back to try to see where we are. After a century of effort, technological advances have finally provided the kind of powerful data sets we really need to accurately measure the properties of the universe. Individually, these data sets have yielded many of the fundamental cosmological parameters, but taken together, they provide a stunning degree of agreement and coherence. It seems that a relatively straightforward theoretical framework provides all we need to match the data. It's an expanding Euclidean universe with 5 major constituents. These constituents were spread about almost homogeneously, but not quite. An initial spectrum of roughness is amplified by gravity to generate the structures we see on the microwave background and in the distribution of galaxies. The theory has about half a dozen primary parameters and about as many secondary parameters, and almost all of them have now been measured to an accuracy of between 5 and 10%. Here they are, the concordance model parameters and their uncertainties. They're the universe's vital statistics. They encode much of the universe's overall character, or at least they define the stage on which the play unfolds. I think one way to view these numbers is a bit like the first post-Copernican estimates of the sizes and shapes of the planetary orbits. The numbers may be refined in the future, but the overall framework is almost certainly correct and is here to stay. I think more than anything else, It's been this amazing convergence on a single set of values from such different data sets that has really galvanized the astronomical community. One might even suggest, I think, parallels in the reactions to Newton's theory of gravity or Darwin's theory of evolution. With each, so much sort of falls into place and is explained that the theories are seen to be clearly on the right track. But of course, with all these theories, there is also room to grow. In Newton's case, it was general relativity. In Darwin's case, it was genes. And this is no less true for cosmology. Just consider the following questions. Why do we have the components we do? Why is the geometry so special, being flat? Why is there initial roughness? And why is there something and not nothing? Yes, we are on the right track, but there's still more of the journey ahead. So where to next? Well, if we want to answer some of these questions, we need to head back to the beginning, back to the first second, where even the laws of physics are being busily created. So come and join me there at the next lecture.